Good afternoon, ladies and gentlemen. I'm Jiamin Zhou from Shanghai Jiaotong University. It's my honor to be here to introduce my latest research, user experience-oriented color scheme adaptation on smartphone displays. As the title suggests, our work is mainly focused on smartphone displays under different lighting conditions. The whole idea comes from our daily life. As the picture shows, the word and the pictures are hard to recognize under a strong light, such as sunlight. And the overbright smartphone screens find our eyes under weak light usually happen at night. This is really annoying. How can we change this annoying situation? That's my work. First, we have to define what a good reading experience is. Here, I will introduce two metrics to help. The first metric is for under strong light. Under strong light is illegible. The readability is degraded. So here I will introduce relative visual performance to help. RVP equals to RT0 over RT. RT0 equals to RT0 is the smallest reaction time a person can achieve. And the RT is the reaction time that this person achieves under a specific condition. So RVP implies how fast a person can react to a specific subject. So, and usually RVP over 80% means good readability. And the second, for weak light, is a finding, and comfort level is degraded. Here, I will use UGR to help. UGR value is provided by International Commission on Illumination. It's calculated by this formula. It's a little complex, but to make it simple, the lower the UGR is, the more comfortable it is. Usually over 25, the UGR value over 25 will make our eyes uncomfortable. So here is two metrics I want to introduce. So let's see. We want to see how these two metrics help in our experiment. We conducted a survey. We recruited 206 volunteers to help to see the exact RVP value and the UGR value under different lighting conditions. The upper half is under sunlight. The lower half is under weak light. As the chart shows, we can see that the average of RVP value is lower than 80%, which hurts readability. And the UGR value, we can see that is over 25, which will hurt comfort level. So let's come back to the original question. How can we change this annoying situation? The existing solution is auto brightness control system. It's like this one, which we are familiar. It can raise the backlight when the ambient light is strong, and lower it when the ambient light is weak. But our survey found that it does improve the experience, but only slightly. For example, RVP is slightly improved, but still under, here is 80. It's still under 80%, and the UGR value is reduced, but haven't reached down to 25. So overall, the automatic brightness control system can't meet our demands perfectly. So we want to make an improvement. To make a further improvement, we must know the factors that will affect RVP and the UGR value. So what are the factors? For RVP, it is mainly affected by the luminance contrast between the foreground color and the background color. And we found that RVP value is positively related to the luminance contrast. And when contrast is over than a certain value theta, the RVP value will reach 80%, which will satisfy the requirement. According to the luminance contrast, we also found that color hue is an important factor, and the RVP will reach the highest. The RVP value will reach the highest when the R equal to 1 and the color hue difference equal to 180 degrees. As to what these two parameters are, we will introduce in the next slide. And the UGR value. UGR value, by its formula, we can know that UGR value is positively related to the total luminance of the smartphone screen. So these are the factors that will affect RVP and UGR value. How can we coordinate all the factors? Here I will introduce a color space called DKL Color Space to help. DKL Color Space shows like this. DKL uses 3 axes to describe this color space: S-axis, LM axis, and achromatic axis. And for any given plane perpendicular to the achromatic axis, this plane the color on this plane have the same luminance. And the biggest of the plane, the biggest of them is called the isoluminant plane. Is this certain plane? But we usually don't present a color in these 3 dimensions. We often use a spherical coordinate to present a color, like this one in alpha, H, and R. Alpha means the elevation from the isoluminant plane, and the H can stand for the hue, and the R is the radius. This R is on the last slide. That when R equals to 1, the RVP can get the highest value. So why we use this DKL color space? Because this color space is it can help us to distinguish the luminance effect and from the color effect. For example, if these two points are 2 color, then we can easily calculate the luminance contrast by calculating the distance between these 2 planes, because all the color on this plane have the same luminance. So this color, the luminance of this color is this plane, and the luminance of this color is here. So the distance is the luminance contrast, and the color hue is easy to be easy to be presented by the H parameter. So using this color space, it's easy for us to distinguish these 2 different effects, and thus conveniently for us to reach the perfect reach the optimal state. So here we need to reflect all the factors we have already talked about to this DKL color space. So how to reflect those factors into here? We have already mentioned that contrast must over theta, which means the color we want to select will be in this gray area, because this contrast is theta. And second, we say that RVP get the highest when the R equal to 1. R equal to 1 means that the color will be on the surface of this sphere, and the color hue difference is equal to 180 degrees, which means the foreground color and the background color are symmetric from this achromatic axis. So these are the factors we have already talked about. But will RVP and UGR enough? Here, as our survey proceeded, we found that there is another factors very important. It's called is similarity. Why similarity is important? Because the similarity is the similarity between the original web page and the web page we alert. It's important because if we alert the web page too much, the web page will seem very strange, and the user will feel very uncomfortable. And the similarity can be represented in the DKL color space too. It's related to the spherical distance between 2 color points. Also, if these 2 points are 2 color, the distance can in some way to represent the similarity. We want to maximize the similarity for user experience. That means we want to minimize the spherical distance of these 2 points. So far we have already modeled all the factors on the DKL. So now is the algorithm part. We have already modeled all the factors. Then here is how the algorithm go. If this point is the original world color, xx1, first the factor is R equal to 1, then just move it along L to x1 star here, and then we want it meet the RVP requirement, then we move it along L dot to x1 dot, and this x1 dot is the new color for the for this original color. And how about background color? When we have this word color, the background color is selected by moving it there. Because the color hue difference should be 180 degrees, so they are symmetric from achromatic axis. So this new color pair will be selected as the optimal selection. But there is a problem because usually there are several word color in a web page. There is maybe have red, have blue, have green. Then there will be several background color. This is ridiculous. The background color must be one. So how about this kind of situation? When we select many background colors, then we just calculate the weighted average of them to get the only one background color. So this is the method we solve this. And how about under a weak light? Under weak light, UGR is more important because a strong luminance might offend our eyes at night. So we want to reduce the luminance of the screen, both word and background. And because the background occupies the most of the screen, so we select black for background color because of its lowest luminance, because its lowest luminance level. Besides UGR, we also have to consider RVP and similarity. We also need to make sure that RVP is over a certain value X and the similarity is as high as possible. So we may change word color accordingly. How about the algorithm for weak ambient light? It's similar to the previous one. If the original color is here, we just move it to the x1 dot because r equal to 1, and then move it along L dot to x1 double dot because RVP should be over x, and make sure the similarity is as high as possible. And then we select the x1 double dot as word color, and the black is set for background color. And here is a problem too, because this color is this color is regular, so we can move it here and then here. But there is a type of color called achromatic color, which means it doesn't belong to any color hue. It's in the achromatic axis. It's on the achromatic axis. When we move it along L, we will get to black. Then, because black doesn't belong to any color hue, we can move it into any direction. So we need to determine a certain direction for achromatic color. For this, we did an experiment. We move it into several directions. And for each direction, we get a lowest alpha to meet the RVP value and the similarity requirement. Sorry. And then we got the result like the left figure. For each different color hue, we got the different minimal alpha, and we want to make sure that UGR is as low as possible, and UGR is positively related to the luminance of the screen. So we just need to find the lowest alpha mean in this figure. We found that alpha reaches the lowest when the color hue is equal to 90 degrees, which means it's the green color. So we select green for the achromatic color. So in a web page, if the color is achromatic color, and under white light, we will move it along the green color hue, this direction, to get a new color. So the algorithm part is done here. We are ready to put it into practice. So we devise this system called ColorVert, and the ColorVert have three parts. This is the workflow of this system. The first part is sensing part. In this part, the sensor embedded in the smartphone will sense the lighting condition and gather the lighting information to the transforming part. And in transforming part, the unit will choose the proper algorithm according to the light information passed by sensing part, and then it will calculate the new color pair and pass it to the final part. The final part executing unit will use this new color pair to exchange the original color pair, and the improved user-friendly web page will unfold to our eyes. Let's see what we will got using ColorVert. There are 4 web pages. The first one is the original version of the web page. And when we put the smartphone under strong ambient light, we will get this one. And when we move it to an even stronger lighting condition, we will get this one. Maybe it looks similar in this lighting condition because we are looking at it under a normal light, not in an extreme light. But actually, it does improve. And blue, if you look carefully, the blue is becoming darker and darker. And this one is under weak condition. As we can see that the achromatic color have already converted to the green. Actually, it's better when we use it on our smartphone and in the specific lighting condition. We have this confidence because we conducted a further survey to prove it. We gathered the volunteers again to do the same experiment as we did before, but this time we showed them the smartphones with the system ColorVert, and here is what we got. You can see that the RVP value is increased significantly, and most of RVP value is over 80%, which means it's good readability. And the UGR value is significantly reduced. Here is all of them are lower than 10. Overall, the score, the preference score, and both strong light and weak light condition is the highest using our ColorVert than the original version. So this is the evaluation part, and we also did some evaluation on its transforming speed to further prove ColorVert's practicality. We did this experiment on four popular smartphones, and we found that most transformation time in 30 minutes. In 30 milliseconds. And it doesn't hurt user experience because it's just done in a few duration. So then we reach the conclusion part. First, our main contributions are as follows. The first, we found that user experience is mainly determined by readability, comfort level, and similarity. And then according to that, we design and implement a system called ColorVert, which can adjust web page color scheme dynamically according to ambient environment. And finally, by the evaluation part, we found that ColorVert can significantly improve user experience compared with the auto brightness control system. So that's the end of my presentation. Thank you for your attention.